Okay, the first kind of rate times time equals distance problems we did were the ones where the distances are equal for the two situations. So Susan left Bob's office crying at 10 a.m., going 10 kilometers per hour. At noon, Bob got his lunch break and was able to run after her. If he caught Susan at 2 p.m., how fast did he run? The key takeaway is that Susan and Bob start in the same place and they end up in the same place. They both start at the office, and Susan runs somewhere, and Bob runs to the same place, and he catches her, which means they have both gone the same distance. So their distances are the same. So let's just write that down. Same distances. So I'm going to fill in this chart to organize all my information about their rates, times, and distances. And right here, I'm just reminding myself their distances are the same. Okay, so what does it tell us about Bob? Susan, well, let's start with Susan, I guess. Susan left Bob's office crying at 10 a.m. That does not tell us her time. It just tells us what time she left. Her time is going to be a number of hours, so that's not telling us her time. But we do know that she's going 10 kilometers per hour. So that is her rate, and we will put that right here. At noon, Bob got his lunch break and was able to run after her. If he caught Susan at 2 p.m., how fast did he run? All right, we don't know Bob's rate, so we're going to call it R. Their times actually are here. Susan leaves at 10 a.m. and Bob catches her at 2 p.m. So her time, she starts at 10 and she goes all the way until 2, which is 4 hours. So starting at 10, 1, 2, 3, 4 hours that she has been running. So that's 4 is her time. Okay, it tells us that Bob left at noon. So his time is just going to be from noon to 2, which is just going to be 2 hours. So his time is 2 hours. So in this problem, they totally gave us the times, even though we might not have noticed it at first. Okay, so we know, since rate times time is distance, we know that Bob's distance is 2 times R, and Susan's distance is 10 times 4, which is 40. And since we know their distances are equal, we can say that 2R is equal to 40, and R is equal to 20. What is R? Look back at your chart and you can see that R is Bob's rate, and this is in kilometers per hour. So Bob's rate is 20 kilometers per hour. So that's Bob. But what does the question ask for? It says, if he caught Susan at 2 p.m., how fast did he run? Well, that's what they're asking for, so that's the answer. But you always have to go back and make sure that you're answering whatever question they asked and not just whatever you happen to get. All right, so that would be how you would do that problem. Okay, here's another problem where you'll find out that the distances are the same. So Roger made the trip on Sunday and Judy made the trip on Monday. Roger traveled at 12 miles per hour. Judy traveled at 20 miles per hour. So her time was 2 less than Roger's time. How far did they travel? Okay, how do I know their distances are the same? Because it says Roger made the trip on Sunday. Judy made the trip on Monday. So the trip is the same trip. So it's the same distance. So same distance. So this is one of the first things you have to find out in the problem is, what is the relationship between their distances? Is one going further than the other? Is one going the same amount as the other? So we need to check on that right away. So now we're just going to fill in whatever information the problem gives us into this chart where we have each person's rate, time, and distance, and we're remembering that rate times time equals distance. So Roger made the trip on Sunday. It doesn't matter what day it was. Doesn't matter at all. Judy made the trip on Monday. Still doesn't matter. Roger traveled at 12 miles per hour. That is Roger's rate, so we can put that in the table. Judy traveled at 20 miles per hour, so we can put that in for Judy's rate. Her time was 2 less than Roger's time, so we don't know either one of their times. They don't tell us anything about their times. So I'm going to call one of their times T. I'm going to call Roger's time T. It doesn't really matter which one I call T, but I have to write the other person's time in the right relationship to that T. So it tells us that her time was 2 less than Roger's time. So I'm calling Roger's time T, which means that Judy's time is T minus 2 because her time is 2 less than his time. All right, so now I'm going to use rate times time equals distance. 12 times T is Roger's distance, rate times time. Judy's distance is 20 times T minus 2. So now I've got my whole chart filled in. I've got everything in there. Now I'm going to use this fact that their distances are the same. And I'm just going to write an equation using the stuff that I put in the distance boxes. So 12T is equal to 20 times t minus 2. Distances are equal. Now I'm just going to solve for t. I'm going to use the distributive property. Negative 8t is equal to negative 40. So t is equal to 5, and this is hours because it's time. All right, what is the question? The question is, how far did they travel? So t equals 5 hours is not the answer, because the answer has to be a distance. How far is this trip they're taking? All right, and all we need to do is take that t and go back and figure out the distance. So 12t would be Roger's distance, so that's going to be 12 times 5, and that is going to be 60 miles. That's how far they traveled, 60 miles. Okay, so this is the second kind of uniform motion problem we did, where we had total distance this time. We could figure out their total distance. So Joe walked part of the 60 miles to London and rode the rest of the way on his scooter. He walked at 3 miles per hour and rode at 9 miles per hour. If the total time of this trip was 8 hours, how long did he walk? So here they're telling us his total distance, because what they're doing is they're telling us he is going to go to London, which is 60 miles away. He's going to walk part of the way, and he's going to ride part of the way. So if you add up his distance riding plus his distance walking, then you're going to have that total distance, which is 60 miles. So that's the kind of problem this is. It's the kind of problem where we can tell what the total distance is. So what does this problem tell us? It tells us that the total distance is 60 miles. So I'm going to first of all just circle that to remind myself that the total distance is 60 miles. All right. He walked part of the way and he rode part of the way. So I have those two rows in my table. And then he walked at 3 miles per hour. So that's his rate walking, was 3 miles per hour. His rate riding was 9 miles per hour. And if the total time of the trip was 8 hours. So I don't know the times of either one. When I don't know either one, I'm going to call one of them t. And I'm going to call the other one whatever I need to call it so that it works with what they're telling me about the time. And this one, they're telling me the total time is 8 hours. So if the walking time is t, then how am I going to figure out what the other time is just by knowing that the total is 8 hours? Well, we'll just think of an example. If he walked for 3 hours, he didn't, but if he did, and it was a total of 8 hours, how many more hours did he need to walk? That would be 5. But how did you figure that out? You subtracted 3 from 8 to get 5 in your head. You didn't think about it, but that's exactly what you would need to do. If his total was 8 hours, one time we could call t, the other time would be 8 minus t. Because whatever t is, if it's 2, it's got to be 6 for the riding. If walking is 5, riding has to be 3. So this is how you write 2 times when you don't know either one, but you do know the total of the times. So now we've got their rate and their time. We can use those to write their distances. So the walking distance is rate of 3 times time of t. The distance riding is 9 times 8 minus t, rate times time. And now what am I going to do with that? Well, they tell me that the total distance to London is 60 miles, which means the distance walking plus the distance riding, that's got to add up to 60. So 3t plus 9 times 8 minus t is going to equal 60. So just multiply it out. 3t plus 72 minus 9t is equal to 60. 3 minus 9t is negative 6t. And then if we subtract 72 on both sides, we have negative 12. So the time is 2, and that is his time walking, because that's where that is in the chart. So how long did he walk? That's exactly what they just asked us, so that's all we need to know. T is 2 hours. Okay, so Bob and Susan decide to meet at a cafe to talk about their science project. They live 54 miles apart. Bob began traveling to the cafe at 8 a.m. at 3 miles per hour. 2 hours later, Susan set out to meet him. If they met at 4 p.m., how fast did Susan travel? So this one, again, their total distance is what you're looking at, because here's the situation. They leave from their houses, which are 54 miles apart, and they head toward each other. So Bob's distance plus Susan's distance adds up to 54, because they're going to meet somewhere in between their two houses, and their two houses are 54 miles apart. So again, you just have to read the problem and kind of get an idea for what's going on, and maybe draw a picture, help yourself understand what you know about the distances. All right, so we're just going to fill in the chart the way we have been doing. So they live 54 miles apart, so that's their total distance. I'm going to circle that to remind myself that that's the total distance. Bob began traveling to the cafe at 8 a.m. at 3 miles per hour. So that tells us Bob's rate is 3 miles per hour. Doesn't tell us his time. 2 hours later, Susan set out to meet him. If they meet at 4 p.m., how fast did Susan travel? All right, so we don't know Susan's rate because it says how fast did she travel, so we're going to call that R. And then we might call one of their times T, except if we look carefully, we can see that we actually know both of their times because we can see that Bob began traveling at 8 a.m. and they meet at 4 p.m. So if he starts at 8 a.m., they meet at 4 p.m. That's 8 hours. 8 to 4 is 8 hours because 8 to 12 is 4, and then another 4 makes 8. So Bob's time is 8 hours. And Susan leaves 2 hours later, so her time is 2 less than that because she wasn't walking that whole time he was. So 6 hours for Susan. And now I know that Bob's distance is 24, 3 times 8, and Susan's distance is 6R, and I know that those two distances add up to 54. So now we just solve for R. We'll have 6R is equal to 30, so R is equal to 5 miles per hour. And that is, if we look at the chart, that is Susan's rate. And that is exactly what they're asking for. So that is the answer. Okay, so this is the last kind of uniform motion problem we have done. You have two people heading in the same direction, and one of them is ahead, one of them is behind. And so that looks like this kind of situation right here. So this problem says Josh began the journey at 6 a.m. at 50 kilometers per hour. Alex began to chase him at 10 a.m. at 60 kilometers per hour. What time was it when Alex got within 40 kilometers of Josh? So let's just fill in what we know. Josh began the journey at 6 a.m. We don't know what his time is. At 50 kilometers per hour. That we know is his rate, so we can put that in the rate box, 50 kilometers per hour. Alex began to chase him at 10 a.m. We don't know what his time is. At 60 kilometers per hour, so we do know that. And the question is, what time was it when Alex got within 40 kilometers of Josh? All right, so a few things we don't know. We don't know their times, but we do know something about their times. We know that Josh left at 6 a.m. and we know that Alex left at 10 a.m. So we can call one of their times T. We'll call Josh's time T. And so therefore, what is Alex's time? Well, let's think about it. Josh left at 6 a.m., so he left first. So he's going a long time before Alex even starts. So definitely Josh's time is more than Alex's time. And so how much more is it? Well, if Josh left at 6 a.m., Alex left at 10 a.m., that's 4 hours difference. So Alex's time is Josh's time minus 4 hours. And now, what do we know about their distances? Well, we know that Josh left first, so he's ahead before Alex has ever even left the house. Alex leaves, and we want to know what time it is when he gets within 40 kilometers of Josh. So he's still behind. All right, so we're going to call Josh's distance D. And therefore, Alex's distance is going to be D minus 40 because Alex is behind and he's within 40 kilometers of Josh. So now, this time, instead of putting 50t in the distance box and putting 60 times t minus 4 in the distance box, we put these relationships between their two distances. So what are we supposed to do now? Well, now we're going to write two equations based on these two rows because we know rate times time equals distance. So 50t is equal to d, and 60 times t minus 4 is equal to d minus 40. So I have two equations and I have two unknowns, t and d. And so the easiest thing to do here is substitution because you know that d is 50t. So everywhere you see a d in the second equation, you can just go ahead and put 50t. So I'm going to put that in the second equation. So I'll have 60 times t minus 4 is equal to 50t, which is d, minus 40. Now I multiply 60t minus 240 is equal to 50t minus 40. Move the t's to the left and the constants to the right. I'll have 10t is equal to 200. So t is going to be 20, and that is time. So that's hours, 20 hours. And that is, if you look back at your table, that is Josh's time. So we need to look at what time Josh left. Josh left at 6 a.m. If he goes for 12 hours, that's going to be 6 p.m. So if he goes from 6 to midnight, That's another 6 hours. And then, so that's 18, and then 2 more hours past midnight is going to be 2 a.m. So 2 a.m. is what time it is when Alex gets within 40 kilometers of Josh. Okay, so now we have when the sheriff began his pursuit, Robin Hood was already 7 miles out of Nottingham. So that's the picture we have down here at the bottom. The sheriff is starting from Nottingham back here. Robin is not in Nottingham. He's already way out here. He's got a head start. So he is 7 miles out of Nottingham already when the sheriff leaves. If the sheriff traveled at 6 miles per hour, that's the rate of the sheriff. We will put that in the rate box here. Robin Hood's rate was 2.5 miles per hour, so we'll put that here. How long did it take the sheriff to catch him? All right, so in this problem, when it says how long did it take the sheriff to catch him, we have to go back and see what they're saying about the time. It says when the sheriff began his pursuit. Robin Hood was 7 miles out of Nottingham. So the sheriff is getting ready to start his pursuit. Robin's over here. We're getting ready to start. It's kind of like a race. So he's going to start chasing Robin. Robin is going to start running from him at the same time. That's what these words are implying. And so it's implying that their times are the same, just like in a race. They started at the same time and they're going to end at the same time whenever the sheriff catches Robin. So their times are equal. We know that the sheriff's distance, if we call it D, we can call the sheriff's distance D. We know that he had to run 7 miles that Robin Hood never had to run. That means that Robin Hood's distance is 7 less than the sheriff's distance. So the sheriff's distance is D, so D minus 7 is going to be Robin Hood's distance. And now we're going to do what we did in the last problem. We're just going to write two equations with T and D in them. So 2.5 times, and I'm not going to write 2.5 because it's not a good idea to work with mixed numbers. I'm going to go ahead and write it as 2.5. You could write it as 5 halves if you want, but working with mixed numbers in equations is not a good idea. So 2.5t is equal to d minus 7, and 6t is equal to d. So again, I'm going to use substitution to solve this system of equations. So I will have 2.5t is equal to d, which is 6t minus 7. I'm going to subtract 6t on both sides, so I'll have negative 3.5t is equal to negative 7. So t is going to be 2 hours. And what is t? It is the time. It's just the time because they both were going at this for the same amount of time. And so it took 2 hours for the sheriff to catch him. How long did it take? 2 hours.